Welcome, everyone, to those who are trickling into today's webinar. All right, now I would officially like to introduce Matt Hurley, the General Manager of MAGSA, to tell us why is this topic important? What are we talking about today? And what's going on in MAGSA related to meters and data?
Good morning. Thank you, Ashley. Thank all of you who are online and taking part in this webinar today, and thank all of you who've attended the previous webinars in the series. It's been a great collaboration with Fresno State Center for Irrigation Technology. We have the rock star of them all, Charles Hillier, here today to talk to you about meters and how those are kind of the starting point in irrigation data and the management of that data. But I'm really looking forward for MAGSA to continue its role as sort of a data leader as we move forward. And the question obviously first comes up is, why do we need data? Charles, if you'll bump it ahead one and we'll give the big answer. You can't manage what you don't measure. It's kind of a cliche these days, and it's easy to say, but if you really boil down to what data is and what irrigation is, it's a math problem. And if you don't have legitimate math numbers to plug into your algorithms and your coefficients, you can't manage it to the precision that you need. I was telling Charles before that we applied for a Bureau of Reclamation grant, and we just didn't get it for the first three times, and so finally I just dropped the niceties and said, look, folks at the Bureau, you need to know where we're coming from. And the first line of the executive summary, I'll read it. It says, estimates and educated guesses are the tools of fools when attempting to hone the efficient consumption of either water or energy in a limited supply regime. And the key thing there, which sort of makes today different than historical past, is it is a restricted supply that we're dealing with, both of water and energy. Uh, you can click ahead, Charles. The critical nature of informed irrigation decisions in a restricted environment is the difference between survival and not survival in a very competitive marketplace for water. We have to know exactly how much is going on, just like you wouldn't want your surgeon working on any of the parts of your human body without all of the testing and data ahead of time, because who knows, you might get a new limb on the wrong part of your body if they get the things going. So same thing here. I mean, if you put too much water on, you can actually cut down your production. If you put too little water on, you can also cut down your production. So what you're always looking for in agriculture is that sweet spot that allows for the proper amount of irrigation so that the maximum efficiency is maintained, and of course the maximum production for that use of that water. Next one, Charles. Accurate data. Data in a database system can be really useful or it can be terribly harmful. And really, the accuracy and the veracity of that data are what's required to defend whatever you're using that data for. In the water world, one can simply say, well, I use plus or minus 20% of whatever, the satellite tells me I'm using. Well, that's fine in general academic sense, but when you get down to the ground and you're in a GSA and that GSA works its way into an allocation regime and you only get 0.75 to 1.5 acre feet per acre for irrigation for the year and you're only groundwater, boy, 20% plus or minus just doesn't make it. As little as a 5% variance can really make a huge difference in the application of irrigation water in modern agriculture. So, the example, I had one example here, just simple numbers, 100 acres. If someone's, takes the agronomic numbers that come out of Sacramento or out of the universities, it might say that on average, 4.4 acre feet of water per acre is what's necessary to grow your almonds. Well, maybe yes, maybe no. If everybody could get that, they'd be thrilled, I'm certain. But the reality is that many farmers use much less water, and perhaps let's say 3.5 acre feet per acre on the same 100 acres. It's a difference of about 90 acre feet per year just in that calculation. Multiplied times 100,000 acres, and you're starting to talk about a substantial amount of water. And if that calculation is what's being utilized to cross-check what your allocation is, it can be killer. It can put you out of business. So again, that's really, really important that we have accurate data for that purpose. Second idea would be we need to have this accurate data because we're going to do a marketing program, say, for example, in McMullen. If we're going to market that allocated water, and if you're allocated 2 acre feet per acre and you have some water left over after the year because you went fallow for a part-time or you planted a new crop, you're going to want to try to, sell some of that water to your neighbor who needs a little extra. And if you haven't kept that data and kept that meter data in a sound and defensible database, you won't have anything to sell because you won't be able to prove up that water quality and quantity, excuse me. And last but not least, Sigma is going to reign supreme for the next 15 years at least until 2040 when we must reach that sustainability plateau. And we're hoping to get there sooner. And we're hoping to aggregate all of the data off of our 100% metered and measured wells within McMullen so that we can, at least on behalf of our McMullen landowners, look any regulator in the eye and tell them exactly how much water we're using and how we're maintaining our sustainability numbers in accordance with our groundwater sustainability plan. So it's really, really, really important that accurate data be available to us. And of course, a meter is the first and foremost way to do that. It's the start place. It's the input for how much water comes out of the planet. Once you start using some of the other sensors in the equations and really start getting an idea right down to the plant level how much water is being utilized, then you can honestly say that you have full control of your operation, just like any other person in any other business would want. So once again, summarizes it really simply. It does require measurement to manage. And I think there's a slide, Charles, for McMullen, simple summary. We hope to be one of the most data-driven management GSAs in the state of California. We have tremendous collaboration and cooperation with our landowners. Those of you who are on here and have attended these other seminars know how important it is because it's been shown to you graphically on several occasions. We have instituted a meter and telemetry program and required our landowners to get to be part of it. Of course, we want to help, and so we came up with a $2.8 million grant that makes that much more consumable and without the pain of the full price. And last but not least, and the most important thing, and that's why our partner Fresno State is so important, is that we need to continually educate our landowners and even our neighbors in the subbasin on the importance of knowing exactly what water we're using rather than estimating and guessing, as I said in my opening summary to the Bureau. So with that, I'll hand it over to the real expert. Enough talk from me. Charles Hillier from Fresno State Center for Irrigation Technology is going to take it and give you all the scientific stuff. Enough from me. Thanks a lot, Charles.
Thanks, Matt. And thank you, Magza, for having me on this webinar. My name's Charles Hillier. I'm the director at the Center for Irrigation Technology at Fresno State. And I'm going to be talking to you today about data-driven irrigation. In particular, I'm going to be talking about the flow meters that are so important in that. Now, if you attended one of the workshops in Kerman or some other extension events, you've probably seen a picture that looks a lot like this. Irrigation scheduling is what data-driven irrigation is all about. It's about managing when and how much water you apply and making sure you do that in a way that works best for your farm. And in general, there are three methods for scheduling irrigation. You can measure the plant, you can measure the soil, or you can measure the atmosphere. So if you're measuring the atmosphere, you're looking at ET. If you're measuring soil, you're measuring soil moisture. And if you're measuring the plant, you're probably measuring one of a variety of different quantities. But all of these things are sort of the first half of the data-driven irrigation scheduling process. Now, they're not mutually exclusive. Two methods is better than one. Using all three is what's best. But all of these data that you're collecting about the demand for water is going to help you decide when and how much water to apply, which is the core task of irrigation scheduling. It's helping you decide about the right amount at the right time. Both of those matter. Now, conventional irrigation scheduling is basically about replacing the water that the crop used with irrigation. And if you watched the last webinar, you heard Dr. English talk about deficit irrigation, which is a very different thing. Irrigation scheduling conventionally is a biological goal that's focused on the plant, whereas deficit irrigation is an economic goal that's focused on profitability and getting returns from water. Whether you're using conventional or deficit or some other form of irrigation optimization, you're doing this in a data-driven way, which means you're taking measurements of the things that are demanding water, plant, and then you're also taking measurements of how much water needs to be applied or was applied. So regardless of which method or which philosophy you're using to schedule your irrigation, a data-driven irrigation scheduling process is always more or less the same. Typically, it starts with getting the data, right? So if you're measuring the soil plant or the atmosphere, you're getting that data. But you also need to know how much water was applied, and that's where the flow meter starts to really become important. Now, once you get those data, then you've got to estimate how much water the crop needs. That's where the math gets pretty heavy, and that's where it's useful to have a tool that can do the math for you. But that's how much the crop wants. It doesn't take into account how much water you have. So when you're doing irrigation optimization, or when you're scheduling under conventional scheduling, you need to also evaluate the constraints. If the algorithm tells you you need to apply 12 inches and you've only got 10, then you're not going to apply 12 because you don't have those other two. But once you evaluate the constraints, what comes out of the end of that part of the process is basically the when and how much, the critical part of irrigation management. And so the last step in the cycle is to actually irrigate. That's where you go out and act. And that is also where the flow meters data is really important because that's where you're measuring how much water actually went out. Just because you planned on applying an inch doesn't mean you actually got an inch into the ground. And a flow meter is going to help tell you at least how much water came out of the ground and went into your field. Now, I've been talking about measuring different things in the atmosphere and measuring how much water you apply. You could think of this as the demand versus the supply. The sensors are going to be telling you how much water the crop needed, or they'll be measuring something that's very closely related to what the crop used. There's a great variety of sensors, and if you attended one of the MAGSA workshops in Kerman, you heard me and a few other people talk about a lot of different sensors. If you attended the first webinar that GIA had, you heard a lot of great stuff about soil moisture sensors. But the other half of that equation is the supply side. And flow meters are the sensor that you need to measure how much water came out of the ground. Now, it's interesting that a flow meter doesn't usually measure flow. It measures something else that's very closely related to flow. And what it measures gets converted through calculation into a flow rate. But the way it measures those things determines how well the meter works in various circumstances. Now, there are other details about how for example, if you're measuring momentum, how that gets converted into flow rate and how it gets reported to you. But all of these meters involve doing some sort of calculation to produce a flow rate. And the flow rate is generally what you're interested in. Also, the way that these flows are measured affects the accuracy and the durability and the veracity of the flow meter data that you get. Now, I'm going to talk about some of the different flow meters that are common in agricultural settings. There are a lot of other types of flow meters that are available that may or may not be relevant to you, but I'm going to focus on the 4 that are definitely relevant to you. And first up is the one that's been around for a very, very long time. It's called a propeller meter. And it's a simple concept. The water's flowing through a tube. There's a propeller that turns. It turns because of the water moving by. So some of the momentum of the water gets transferred to the propeller. There's a sensor in there that measures how often that propeller makes a revolution. And those turns get turned through calculation into a flow rate. It's a reliable device. It's been around for a long time. It's one of those tested and tried and true sensing platforms. It does have some issues. The calibration of a mechanical propeller-driven flow meter is going to drift, and it tends to drift faster than some of the newer electronic meters. Now, that doesn't mean these propeller meters are bad. They're quite good, especially if they're maintained. but that maintenance is very, very important if you want to reduce the changes in calibration. Some of the old propeller meters were entirely mechanical, which is quite nice because they don't require any power, so you don't have to go out and change batteries. But if you want to know what the flow rate is, you actually have to go out to the meter and look at it, which is kind of inconvenient. So these newer models have lower what's called straight pipe requirements, but the older models and some of the models that are still on the market require a significant amount of straight pipe upstream and downstream of the meter. If you don't have that straight pipe upstream and downstream, you're going to be getting erroneous measurements from those meters. Some of the newer ones, like the one in this picture, have a flow straightener, which reduces that straight pipe requirement, but it doesn't make the requirement go away. So you have to take that into consideration when you're choosing this type of meter to make sure you actually have room to install all that straight pipe. Now, the meter that's become very popular over the past several years is the mag meter. The mag meter basically uses an alternating magnetic field to measure the flow velocity. It's nice because it doesn't have any moving parts. It has very low head loss, and it can be installed either as a flanged inline device or as a saddle mount. They have very good calibration stability, so their calibration lasts a long time, and they have shorter upstream and downstream straight pipe requirements. However, these devices must have power to operate, so if your battery goes dead, you're losing data. Now, another type of device that's been around for a long time is the ultrasonic. There's two types of ultrasonic, one called the Doppler and the other called the transit time. The Doppler is special because it requires particles in the water. Those could be bubbles or bits of sand or anything. And so because of that requirement, Doppler doesn't get used too often in irrigation settings because we're dealing with clear water. The more common one is the transit time, and those are the figures you see over on the left. There's some examples of transit time. One of the nice things about the ultrasonic meters is that they're available in a clamp-on format. So you can basically move this meter around from one place to another. Now, that's not very useful if you're trying to record data for irrigation management, but it is very useful if you need a second opinion on whether or not your flow meter is reporting accurate values. I'll talk about that again in a few minutes. Now, the last one is actually my favorite, and it's my favorite because that's what we use in our testing laboratory. That picture you see there with a dark colored device with a yellow pipe, that's actually the picture of the meter that we use in our testing laboratory. It's one of several, and it's a particular type called the Venturi meter. Down here at the bottom, you see is a cutaway of that exact same type of meter. And these meters are nice, and we like them at CIT's laboratory for one simple reason. Their calibration lasts a very, very long time. In fact, the meter that we have installed here, its calibration is guaranteed for the lifetime of the meter. We never have to get it recalibrated. Now, this meter operates by using something called Bernoulli's law, and it basically measures a pressure difference. So there's a pressure tap right there, and there's a pressure tap right there. And it gives you a very reliable measurement of the flow rate going through that meter by measuring a difference in pressure. Now, that means you have to have a pressure transducer, and those pressure transducers have to be calibrated. But that's much easier than trying to get this giant flow meter calibrated because it's quite heavy and it costs a lot to have it shipped around. So Venturi flow meters are available in agricultural settings. They don't get used very often, but they are very stable and they are very reliable, but you do need a pressure measurement. So far I've been talking about the hardware, the stuff that gets wet, but you're interested in data, right? So when you're looking at your flow meter data on your phone or on a website or something like that, you're not actually using just the thing that got wet. You're actually using a flow meter system, and it has several different components in it. The measurement is done by the device, the thing that gets wet, the meters we've been talking about. But there's also going to be some electronics that convert that measurement into data. There's going to be a communications element, oftentimes called the telemetry, and that moves the data out of the field. If it's only in the field, it's not particularly useful because you got to go out there to get it. So having a communications component is very, very useful in a telemetered, in fact, essential in a telemetered metering system. Now, when that data leaves the field, it's got to go somewhere. Typically, it goes into a database, and I'm calling that here the data or the backend, right? So you don't actually look at the database itself. You look at what's called the front end of the user interface. This is basically what you see, right? So that all of these components together are necessary for you to actually see the data on your phone or on a website on your browser. And understanding this system is useful because when you buy a meter, if you only buy the meter, you don't get all of these other things, and so you don't get the data on your phone. But when you buy a telemetry or a flow metering system, you have a couple options. One option, oftentimes the easiest option, is to get one where all of these system components come from the same manufacturer. That simplifies maintenance, it simplifies purchasing, but it does create some limitations that you may not be able to overcome. For example, there may be places where communication options are limited, and that manufacturer doesn't have the communication option that works for you. You may also find that you want to use a different website other than what the manufacturer provides. So it is possible to mix and match and choose best of breed components for each one of these elements in the system. But if you do that, it has to be you that does it. So it's extra work for you. Now, when this data gets up into the cloud or when its calculations are being done in the meter itself or in the telemetry system, there's a lot of data processing that happens. And it's important to understand a couple of the key things that happen in data processing. First of those is the sample rate. The sample rate's pretty simple. It's the number of times that the meter measures the flow or measures the thing related to flow with respect to time. Now, the sample rate is oftentimes higher than the data that you actually see. So the data that you actually see is based on the reporting rate. Many types of meters will take lots and lots of measurements and average them together. That improves the accuracy of the data that gets reported to you. It also improves the stability of the data that gets measured. Some of these measurement technologies, there's quite a bit of noise, but you can get rid of that noise by taking a lot of measurements and averaging them out. And that's what's being reported to you. So if you're getting data that's reported to you once an hour, your meter may actually be sampling at a much higher rate than that. Now, there's another important data processing step that we're going to talk about quite a bit more later, but it's important to remember that that aggregation, which is where you're basically grouping the data and in most cases just adding it up. But that aggregation step is a really important part of the process. Now, I talked about the reporting rate. What exactly does a meter report? It's probably many of you have heard of flow meters and you've seen flow meter data, and you know flow meters report gallons per minute. But they don't all report gallons per minute, and many of them, especially the newer ones with more advanced electronics, report a lot of different things. Most of the meters that are available to you in MAGSA are going to have a totalizer in them of some kind. And so they can actually report two different numbers, the flow rate, which is the instantaneous flow rate, or the total volume that's flowed through the meter. That total volume that's flowed through the meter depends on some starting point where you start adding up the data. That's when aggregation becomes really important. Typically, if you don't change anything, that's going to be from when you first installed the data. I also want to point out that the meters that we're focused on today are meters that are marketed for the American market. And so you're going to see units like gallons per minute or acre feet per day. But if you buy a meter that's targeted towards the European market, you may also see things like liters per minute or megaliters per day. Same thing's true with the total flows. For meters that are meant for the US market, you're going to see acre feet or acre inches. But if it's a European meter, you might see megaliters or hectoliters. And there's a reason why those are starting to pop up. There is a standard, an international standard, ISO 16399, which was changed recently. It's the standard that dictates how to measure the accuracy and the performance requirements of agricultural flow meters. And that standard now requires that any meter which complies with this standard be able to report many of these units. And at a minimum, it has to report the SI units, megaliters, liters, hectoliters. That's significant because some of the US manufacturers also want to sell their meters in the European market. And so they have to add these features if they want to comply with that standard. Now, there are many other quantities that get used for reporting flow. They're used in other contexts. For example, in urban users might be looking at megagallons per day. If you're in some industrial processes, you might be looking at, rather than gallons per minute, you'd be looking at gallons per second or liters per second. So there are other quantities, and those are not typical for agriculture. Generally, you don't need to worry about it. But if you buy a meter that's intended for a different market other than agriculture, you may need to spend extra time making sure it's reporting the units that you expect. Now, one of the really important things about a flow meter is that it be accurate. If you're getting data out of this flow meter and it's not accurate, it's not data, it's noise. MEGSA has a very specific accuracy requirement, which the meter must be accurate to within 2% of the reported flow. It's important to understand that that's the instantaneous flow rate accuracy. All the meters that are available to you as part of the MEGSA program comply with this 2% accuracy requirement. Some of the meters that I mentioned earlier on, like the ultrasonic and the Venturi, are quite a bit more accurate than this. There are ultrasonic meters that are out on the market now that are accurate to within 0.025%. It's also important to understand that the accuracy of the flow rate is not exactly equal to the accuracy of the totalizer. Now, the math behind this gets pretty complicated, and there isn't a big difference between the flow accuracy and the totalizer accuracy, but it's important to remember they are not identical. The totalizer accuracy is going to be a little bit worse than the instantaneous flow rate accuracy. Now, this accuracy and the accuracy requirement, that 2%, is important because when you're looking at the flow, what you see is not exactly equal to what's happening. For example, if your true flow is 100 gallons per minute, then the flow that's reported to you as actual is somewhere between 98 and 102. So if you're seeing 98, then the flow rate could be 100, it could be 99, it could be 101. If you're seeing 102 on the flow meter, then the actual or true flow rate is somewhere around 100 or 101 or maybe 103. Also, it's important to note that the reported flow, the precision of that reported flow should be appropriate for the accuracy that the meter has, but it isn't always. This happens on websites that report flow, where the math that's being done on the website is just displaying the result of the math without trimming the extra digits on the end. So for example, in this 100 gallon per minute and 2% accuracy measurement, if the reported flow is 100.123, then those last three digits are really superfluous because the accuracy is more coarse than what these digits imply. So if you're seeing flow meter data on a website or on your cell phone and it's got a whole bunch of extra digits at the end of it, don't assume that those are absolutely correct, because in general, they're not. Now, when you start getting your flow meter data, first thing you're going to ask yourself is that number right? So it's important to have some expectation of what the flow rate should be. And the best way to get that is to get your design documents. And I'm going to show you an example from Fresno State. Fresno State Farm recently installed a new almond archer. It was a couple of years ago. And when they did that, they actually had a design firm design the irrigation system for them. And this is one of the design documents that the university received. It's a map. It shows where all of the main lines are. It shows where the fields are and the blocks within the field. And it also included some very important summary information that I've expanded here on the right. And the number that you need from this design document is the expected flow rate. So this is the flow rate that we expected when the irrigation system was installed and it was new. This is your best bet to getting your initial expectation of how much water the irrigation system is going to deliver. Now, if your system is older, that's still a useful number because it sets the baseline for your expectation. But as systems age, their flow rate is going to change. For example, if you got pressure regulators in the system, pressure regulators age too, and their ability to regulate pressure changes as they get older. So that might make the flow rate go up, it might make the flow rate go down, and you won't know until it's too late. Elevation definitely has an effect on flow rates in uncompensated systems. Block size obviously is going to make a big difference. Clogging, the bane of every drip system, is going to reduce flow rates. And as the aquifer level declines, your flow rates are going to decline. So having this expectation about the flow rate is very, very useful, not only to give you confidence that the flow meter data you're getting is correct, but also to help you better understand the performance of your irrigation system. If you've got blocks that are slightly different sizes, you're going to consistently see slightly different flow rates as you irrigate that whole field. Now, if you don't have pressure regulators or you don't have pressure compensating emitters, your flow rate and the relationship between flow rate and the pump is much more complex. So complex that you need to have a calibrated meter measure your flow. That calibration is really important. Uh, Using a calibrated meter means that the measurement that you get from the calibrated meter is traceable back to a very, very, very reliable reference flow meter. And so you can show the traceability of how the measurement that you got from that calibrated meter relates back to the very, very accurate meters that are in laboratories. The other thing you can do is consult with an engineer. An engineer can do a lot of calculations and help you understand what kind of performance you should expect from this meter or from this system, and especially what kind of flow rate you should expect. So if you're dealing with unregulated systems with non-compensated emitters, you should pay more attention to what the flow rate is and make sure you get a measurement to confirm that your meter is generating the correct numbers. Now, earlier on, when I talked about data processing, I mentioned aggregation. I said I was going to say a little bit more about it. And this is it. Aggregation is basically grouping the data together and then computing some number about that group. The most common one, the one that you're going to see almost all the time, is the totalizer. It's basically the sum of the data. And by default, almost all meters are going to all metering platforms or metering systems are going to add up the meter data for a particular well, right? Because you have that well attached to a single, or you have that meter attached to a single well. Now, in addition to summing up for the well, you can also get it summed up over certain ranges of time, by day or by week or by month. And we'll see some examples of that in just a second. If you're careful and you've got the data, and depending on how your irrigation system is designed, you can also aggregate by field or even by block. Now, if your well is delivering water to several fields at the same time, you can't do this. But if your well is delivering water to a single field, then you can actually use that flow meter data to do your irrigation scheduling calculations, and you can use that data correctly because that's telling you exactly how much water went to that particular field. And if you're only irrigating one block at a time or one set at a time, you can actually be even more precise and add up how much water was applied to individual blocks. That could be really useful if your blocks are very different in size because it helps you figure out the right water balance calculation for each individual block. Now, several weeks ago, the Sigma Water Analytics folks gave a presentation for MAGSA. This is the firm that's developing the platform that's delivering data to MAGSA and is the platform that's connected to the telemetry on many of your flow meters. So these folks are providing basically the bottom half of that system that I've mentioned. They're providing the data on the back end and the UI that you see. And here's an example of that UI. This was the same thing that the Sigma Water Analytics people presented. And I want to highlight it again here because this chart, this graph, or this image in particular shows the two different ways that we look at flow meter. Here you can see the instantaneous flow rate. And over a period of time where the flow rate's not changing significantly, you should expect to see the flow rate look like this. It's more or less flat, but there's a little bit of noise in the data. You can never make the noise go away completely because there's always noise associated with any sensor measurement. But it should be relatively flat. The other thing this graph is showing is the totalized flow. It's also showing the totalized flow over a couple different time periods. This green line is basically totalized flow over a day. So there was no irrigation early on in the morning. When they started irrigating, the flow started going up right away. There's a lot of different ways you can add up or aggregate the data over different time frames. And the guys from Sigma Analytics showed you different examples that their platform's capable of. It's quite nice. They've got defaults for adding it up by day, by week, by month, by year, and even by water year. And in addition to that, you can actually put in specific date ranges, and you can get totalized flows over date ranges that are relevant to you, like the cropping season or the amount of flow that's happened during bloom. Those can be really useful if you're doing more fine, detailed measurements or management of your irrigation system. And one other thing I want to mention is that you can do a lot with this platform. You can do even more with this spreadsheet. And that's really useful. This system is really useful because they make it relatively easy for you to download something that can plug right into a spreadsheet. If you follow their instructions from their webinar, you can export your data as a CSV file, which plugs right into almost every spreadsheet on the planet. There's something else that this is important for. Nothing lasts forever, and we know that Sigma Analytics is around for the long term, but things happen. And it's always good for you to have a copy of the data. These data are yours. And so you need to save them and back them up and keep your own records. And downloading a spreadsheet or downloading a CSV file is the easiest way to do that. If you make it a habit to at least once a year, go in there and download this CSV file. Now you've got your own copy of the data. You can keep it as secure as you want to keep it, and you can keep it for as long as you need to. So exporting this data is really important for your peace of mind and for backing up, but it's also your gateway to doing all of the other fancy aggregations like by field or by block that I mentioned earlier. So when you have this meter, you can also do some other things with it. In addition to just scheduling irrigations, you can use this meter to detect some problems. For example, if you have a good expectation of what the flow should be, and you see that the flow is actually higher than what you expected, that means that there are a couple different potential problems. These are just two of them. There are others that are less likely. But one problem that you need to deal with right away is that there might be a leak. So if you're seeing the flow is quite a bit higher than what you expected, and it's staying high for the whole time, that means you need to go out there and start looking at the pipeline, looking for wet soil or puddles or streams running off the field, because that means you probably got a leak somewhere. Now, if the flow is higher than expected for short periods of time, that might mean that somebody made a mistake with the sets or the blocks in a set. Maybe somebody turned the wrong valve or forgot to turn a valve or left the valve open. And that can happen when the flow is lower than expected. If somebody didn't open the valve all the way or they opened it late, your flow rate can be lower. But the bane of drippers is clogging. Clogging will always make your flow rate go down. And the other thing, the thing that Sigma is supposed to help us prevent, is that if the aquifer level declines, your flow rate's also going to decline. Now, if you look at the flow rate, the instantaneous flow rate in the graph over time, it will also help you detect if there are timing errors with your irrigation schedule. So if maybe somebody started late or they started early, you can see that in the graph of the flow rate with respect to time. It can also help you detect some unplanned irrigation. Somebody needed to open a valve and they didn't report it to you or you didn't know. You're going to see that in the graph of flow rate with respect to time. And finally, the problem nobody wants to have, but it does happen, is when you expect there to be flow and there's nothing, that means you've got a problem that you need to deal with right away. Maybe you don't have power, maybe the wells run dry, maybe something really awful has happened. So if you see no flow rate when you expect it to be flow, you need to get out there and figure out what's going on, because that could be a sign of something really, really bad. The last thing I want to mention is some of the long-term issues. These flow meters that are appropriate for the MAGS metering program are built to last quite a long time. And calibrations do not last forever. Every meter, no matter how good it is, will have calibration drift over time. The manufacturers are going to have some recommendation somewhere in their product literature telling them how long they recommend you should wait before you get your meter recalibrated. It varies by measurement type. It also varies by manufacturer. It's not something you need to do necessarily every year, but again, that depends on the meter type itself. But you will eventually need to get your meter recalibrated. This recalibration is important because as the meter drifts, it might drift up and it might drift down, and you won't know until it's too late to do anything about it. So following the manufacturer's recommendations about calibration is very essential to make sure you don't run into this problem where somebody says, Joel, your meter is under-reporting and you actually pumped a lot more than that. Also, when you get your meter calibrated, make sure you either get it tested or calibrated at a certified laboratory. So the thing you need to look for is the laboratory ISO 17025 certified? That's a laboratory certification that guarantees that they're doing a good job and that they keep all the records that are necessary to prove that they're doing a good job. You can also get your meter calibrated by an experienced tester. They need to have their own calibrated meter, and you need to make sure that they've done this a lot of times and they know exactly how to do it. Regardless of which approach you take, your meter calibration won't be any better than the calibrated devices that the laboratory or the tester is using. So if their tester has a calibrated meter that's accurate to 3%, they won't be able to calibrate it down to the 2% that MAGSA requires for your meter. So when you choose a meter, a tester, make sure you check how accurate their meter is. Almost always they're going to be using an accurate meter that's more than enough, more accurate enough than what you need. But it's always a good idea to ask. One other problem that you're going to see over the very, very long term is something that I usually call register rollover. When meters have been in service for a very long time, you will see this phenomenon. It doesn't happen very often. It happens several years, where the totalized flow will go up and up and up, and then suddenly it'll appear to drop back down to zero. Now, that totalizer is basically the result of some math, and the math is happening either in the meter's electronics or in the portal in the database on the back end. But regardless of where it happens, there is some maximum possible value that the totalizer can hold. And once the flow accumulates above that maximum value, almost all of these devices go back to zero and start over. And so on a graph, it's going to look like the meter broke, but it didn't. Now, this isn't something that's going to happen every year. It can take many, many years, especially if the newer meters can hold a very, very large value. But if you've got an older meter or you've got telemetry that's older, and you notice that the totalized flow suddenly drops down to zero, that doesn't necessarily mean the meter's broken. It could mean that the totalizer is rolled over. But it's scary to see if you're not expecting it. So just some conclusions. Just as Matt said, I couldn't agree more. You can't manage what you don't measure. Flow meters are a critical component, a critical measurement of data-driven irrigation. These meters are what measures the supply side of the demand and supply equation that you are computing when you do data-driven irrigation. And I also want to highlight that the meters that meet MAGSA's requirements provide you with an accurate and usable data source. There are a lot of inexpensive meters that are out on the market, and they're not very good. So don't let the price motivate you to buy a cheaper meter. You need to buy the meters that work, that are comply with MAGSA's program. And if you do that, you can be very confident that you're getting accurate and usable data. So that's the end of my presentation, and we have quite a bit of time left for questions. So as Ashley mentioned, if you got some questions, please type them into the chat, the Q&A box.
Thank you so much, Charles and Matt, for delivering today's presentation. Charles, that was very thorough. Thank you for making it so relevant for our Maxa growers, even tying in the specific data management platform that they are becoming familiar with. That was excellent. So again, please ask any questions in the next few minutes you have for Charles, for Matt, on anything related to your meters, data, and how to evaluate it. You can raise your hand and I will unmute you or type your question using the Q&A box below. So I'll be quiet for just a moment to allow for your brains to think and write your questions.
Well, as usual, I can't keep quiet on any subject, but Charles, I can't help but be reminded. I always try to simplify things, and when I talk about the water bank, it immediately equates to a checking account and a savings account. And even on the metering side, when you have the two different reporting, the flow and the totalizer, I can't help but think about every one of us, getting quite used to our speedometer and our odometer on our car. And essentially, that's what's happening in a meter. Is it's telling you the speed that you're going, and it's telling you how many miles you've gone over the history of that recording. And that's exactly what we're looking for in McMullen, because that's really, really important. I did kind of bypass and probably should have spent more time on the secure part of this. I think you indicated, Charles, that a lot of times these meters are reported up to the cloud, and as all of us know, a cloud situation is sort of a communications device. The cloud, provides communications platforms. In McMullen, we have using Sigma Water Analytics, we've provided a direct reporting secure system where the data is secure in its transit to them and it's secure when it rests with them, so that each of the landowners can rest assured that nobody's going to come in and mess with their data, and so can MAGSA be assured that that data will be safe and secure when we go to use it to defend our uses under Sigma. So thanks again. I always learn something too, and I really appreciated your information about the meters.
And
We got some.
I just wanted to add that security requirement is really important when you're looking at the system view, because if you're pick and choosing different parts of that system that make it work best for you, that means you've got to make sure that each one of those elements is secure. I've seen a couple different situations where the telemetry was transmitting data and it was unencrypted, but then it got encrypted as soon as it went into the database. And as you mentioned, the Sigma Water Analytics folks are making sure that it's encrypted both in transit, which means as it's leaving the field and going to the cloud, and at rest when it's in the database.
Hmm.
If you're going to build your own system, it's your responsibility to make sure that that's happening.
Hmm. That's great. Thank you so much, Matt and Charles. We do have one question from Colin. He asks, can you talk about pulse counting by telemetry versus accumulating flow meters? Is there a difference? And errors? I think he's asking what are potential errors.
Yeah, so pulse counting is one of the two most common ways that flow meters output their data from the hardware directly. The pulse is basically you see an electronic signal and there's a pulse in the signal, and each pulse corresponds to a fixed unit of water. The other method is called a current loop, where you're basically measuring the amount of electricity that flows through a thing, and that's proportional to the flow. When you're adding up the amount of flow, you're basically counting pulses if you're using a pulse output on your flow meter. That can be tricky if you've got a telemetry system that's counting the pulses and the meters outputting the pulses, because some meters can output pulses faster than the telemetry can count them. That's a pretty rare problem, and it's a design problem, and it's something you do need to be aware of, that if the meter's spinning too fast, you might actually be losing data if you're not using a telemetry system that's adequate for the meter. But when you're adding up those pulses, you're basically totalizing the flow. Many of the meters that have a pulse output actually have a setting in them where you can choose how much flow corresponds to a single pulse. And you can use that to get a finer and finer resolution or precision in the reported instantaneous flow rate.
And then in the case of McMullen, there was some initial issue with the pulse rates, and those have been reduced down to a fairly fine pulse rate, which is 1 gallon per pulse. And so there's a lot of pulses for every gallon. So if it's 1,200 gallons a minute, that means that there's 1,200 pulses every minute that's being reported up into the database, and it is providing that accuracy. The one thing I did want to say, and I always say this to everybody when I get a chance, because with a person using their user interface on their phone or their computer or whatever, if you walk out to the field and you hold it next to your meter, it probably is not going to report for you what's actually happening, because if you just track the information, it goes from the meter into the telemetry device, into the database, and then gets sent back to you again. So there's a lag time that will cause it to be trailing. Whatever's on your interface is going to be trailing what the actual field data is. Don't get yourself confused by that. Use your user interface when you're out of the field. You can certainly use the information right on the meter when you're in the field, but don't allow yourself to be confused by the fact that it looks like it's not reporting correctly. It is. It's just about 5 minutes late, perhaps,
Yeah,
getting to you.
yeah, it's a very common feature.
Yep.
Or I call it a feature, but yeah, it's a very common thing.
It's a thing in meter business, and we're learning more and more about meters and telemetry and communication all the time. And it's amazing how much information can actually be tracked and be put into great use in analysis. So it's really a great addition to the old clipboard and read from the totalizer.
Can't manage what you don't measure.
That's right. Can't
That's
manage
the
what you
thing to
don't
measure,
measure.
remember.
Don't be using those tools for fools. Make sure you're using the best available data anytime, everywhere. And if you're in MAGSA and you've complied with our metering, monitoring, and telemetry program, you will be getting the best information you can possibly get from the field. There's some other sensors too that probably will be added to that, but you gotta have a good number to start from. And of course, I have to report to the state exactly how much water came out of the planet in a given period of time. And so it's extremely valuable from a defensibility for our GSA as we go forward. So thanks to everyone who's already complied. And for those of you who are considering it and haven't done it yet, please get it done. We even have some grant money left. So make sure you don't miss out when that final bill comes in.
I think that's a perfect note to end on. Thank you all so much for joining us this afternoon, and we look forward to seeing you at upcoming Grower Irrigation Academy events. Go enjoy some lunch and have a great rest of your day.